Hello friends, I welcome you in lecture number 30 on hypothesis testing. In this lecture, we will discuss one question on chi-square goodness of fit test. This question was asked in GTU Summer 2021 exam. Now before going for this lecture, I suggest you to watch my lectures on chi-square distribution, and also I suggest you to watch lecture number 29 in which I have explained how to apply chi-square goodness of fit test. And if you have seen that lecture number 29, you can recall that the formula for test statistic for chi-square goodness of fit test is chi-square equal to sigma observed minus expected frequency square of this difference divided by capital E, and we are considering sum over all possible groups or categories. And to find out these expected frequencies, we will use the formula for the probability mass function or probability density function of hypothesized distribution. We have to take care that all the expected frequencies are at least 5. If there are some frequencies which are less than 5, then we will combine them into single categories. We will combine the categories corresponding to frequencies which are less than 5. And we also recall that this chi-square goodness of fit test is always right-tailed test. So with this in mind, we try to answer this question. The number of defects in printed circuit boards is hypothesized to follow Poisson distribution. A random sample of 60 printed boards has been collected and the following number of defects observed. Here the random variable under consideration is the number of defects in printed circuit boards, and we have to test the null hypothesis that this random variable, which we denote by capital X, follows Poisson distribution. The population from which they have taken this 60 printed boards, we have to test the hypothesis that that population follows Poisson distribution. So the population of the number of defects in printed circuit boards is hypothesized to follow Poisson distribution. So this first statement is giving us the null hypothesis for our goodness of fit test. And this is the data for random sample of 60 printed boards. So they have given this data in terms of frequency distribution. This is the number of defects, that is there are this 0, 1, 2 and 3. There are 4 categories. So first category is that there are no defects, there are 1 defects. Okay, so the number of printed circuit boards with 1 defects. There are 9 printed circuit boards with 2 defects. Similarly, there are 4 printed circuit boards with 3 defects, and there are 32 printed circuit boards with no defects. So our sample data is already given in terms of the frequency distribution, and these are the observed frequencies for this data. And because we have random sample of n equal to 60 printed boards, if you take sum of all these frequencies, then it must be equal to 60. Use the chi-square distribution to test the claim that the number of defects follows the Poisson distribution, and they have given this table value of chi-square distribution for alpha equal to 0.05 level of significance and 1 degrees of freedom, and that critical value is given as 3.84. So what is our first step is, first we define that our random variable capital X is the number of defects in printed circuit boards. We assume that capital X denotes the number of defects in printed circuit boards, and we have to test the null hypothesis that capital X follows a Poisson distribution with parameters say lambda, but lambda is not given here, and this is going to be our null hypothesis. So alternative hypothesis will be that X does not follow Poisson distribution with parameter lambda, and they have already given the table value and their level of significance is 0.05. Now because we require value of lambda to calculate the probabilities corresponding to each category, first we have to estimate this parameter of Poisson distribution using the sample data. These are the values of small x, the number of defects, and these are the corresponding observed frequencies which we denote by capital O. And if we have frequency distribution, we are using small f also. Now this parameter is required. We don't know what is lambda and it is not given in the question also. So we have to estimate this population parameter lambda using the sample mean. So this we will estimate using sample mean x bar, and we know the formula for the sample mean of discrete frequency distribution. We have to take product of frequencies with values of variable, and we have to divide by total number of frequencies. So I have to multiply 0 with 32, 1 with 15, 2 with 9, 3 with 4. I have to take their addition and I have to divide by total of all the frequencies, which is 60. So that I have done here. I have written all these things systematically. Lambda is obtained using that sample mean, which is sigma fx divided by sigma f, and it is 0.75. So we will estimate this parameter lambda using this sample mean, and we will consider lambda equal to 0.75 because this turns out to be 0.75. Now once we have value of lambda, we can write the formula for probability mass function of Poisson distribution. We know this formula, e raised to minus lambda, lambda raised to x divided by x factorial. I hope you are familiar with Poisson distribution also, otherwise you will not be able to understand this lecture. So now I can calculate the probability that number of defects are 0, number of defects are 1, 2 and 3, and this observed data gives us the number of defects, values of number of defects, or not values, the frequencies. That is, there are 32 printed circuit boards with 0 defects, there are 15 printed circuit boards with 1 defects, and so on. So this is data from the sample, and we have assumed that our population follows Poisson distribution. So due to that assumption, we can find out the different probabilities. We can find out the probability that there are no defects in the printed circuit board using this formula. Similarly, we can find out the probability that there is one defect in the number of defects in the printed circuit board is 1. Similarly, the number of defects in the printed circuit board is 2. So we can find out the probability that the number of defects in the printed circuit board is capital X equal to probability of capital X equal to X. We can calculate the probabilities that number of defects in printed circuit board is small x for each value of X using this probability mass function. So that will give me the expected probabilities for each category. And if I am interested in the expected number of frequency for each of these category for the given population, then I will multiply these probabilities by sample size n, that is I will multiply with 60 and I will obtain expected frequencies. So using probability mass function, we will decide probability that the number of defects is small x, and by multiplying this probability we will find out expected frequencies. And once we obtain expected frequencies, we will check whether all the expected frequencies are at least 5 or not. And if they are not, then we will combine the required categories and we will make sure that all the expected frequencies become greater than or equal to 5. After that, we have calculated this test statistic, and for that we will require this terms difference between observed and expected frequency divided by expected frequencies. So I have done all these things systematically here, but that is the main idea. I start by taking this notation for capital X. The number of defects in printed circuit boards is denoted by random variable capital X. Null hypothesis is that capital X follows a Poisson distribution, and alternative hypothesis is that X does not follow a Poisson distribution. Level of significance is 5%. Now we are not given the mean lambda of the Poisson distribution, which we have taken as hypothesized distribution, so that we can estimate using the sample mean. So I have calculated sample mean for the given frequency distribution using the formula of sample mean, x bar equal to sigma fx divided by sigma f. So I have multiplied corresponding frequencies with values of categories, and I find that value of lambda is 0.75. So I have estimated population parameter lambda using sample mean, and that turns out to be 0.75. And then I know that a capital X follows a Poisson distribution, because while performing this test we assume that null hypothesis is correct. So under that assumption, capital X follows Poisson distribution, therefore probability mass function is given by e raised to minus lambda, lambda raised to x divided by x factorial. X takes the values 0, 1, 2, 3 and so on. And we have calculated lambda, that is 0.75, which we substitute here. And now we calculate all these probabilities for x equal to 0, 1, 2, 3, etc. For x equal to 0, I will have e raised to minus 0.75, 0.75 raised to 0, which is 1, divided by 0 factorial, that is also 1. So the only contribution is from this term, e raised to minus 0.75. Using scientific calculator, I find this probability as 0.4724. Then I take small x equal to 1 here, and I obtain probability that capital X equal to 1 is e raised to minus 0.75, 0.75 raised to 1 divided by 1 factorial, and using scientific calculator I obtain probability capital X equal to 1 is 0.3543. Then I calculate probability for capital X equal to 2 using this formula for small x equal to 2, and I find that probability that capital X equal to 2 is 0.1329. Now whenever we are using this type of Poisson distribution, we have values of random variable as 0, 1, 2, 3 and so on, and there is no upper bound. So I have obtained first probabilities for x equal to 0, 1 and 2, and suppose I am interested in the probability that capital X is 3 or more, then this I can rewrite as 1 minus probability that capital X is less than 3, because we know that capital X greater than or equal to 3 and capital X less than 3 are complementary events. Now probability that capital X is less than 3, that is equivalent to the fact that probability that capital X is less than or equal to 2, because X is a discrete random variable, so the values possible are 0, 1 and 2, and then I have obtained 1 minus the possible values are probability that X equal to 0, then probability that X equal to 1 and probability that capital X equal to 2. I have calculated all these probabilities, so I substitute them and I find the probability that capital X is at least 3 or probability that capital X is greater than or equal to 3. So this is I just explained. I substitute all these values here which I have calculated using that probability mass function formula that I have substituted, and I find that probability that capital X is 3 or more is 0.0404. Now once we have all these probabilities, we can find out the expected frequencies corresponding to all these possible values of small x. The values possible are 0, 1, 2 and last category we consider as 3 or more. So now we can find out expected frequencies simply by multiplying each of these probabilities which we have calculated for each x. We multiply each of these probabilities by total number of observations in the sample, which are 60, and we will be able to decide expected frequencies. So I have written these expected frequencies here in the table. First I have written number of defects small x. These are the different categories. Number of defects are 0, 1, 2, 3 or more, and these are the probabilities which I just calculated here, 0.4724. all these I have written in the table. And expected frequency equal to n times probability that capital X equal to small x. N is 60, so I have multiplied each of these probability by 60 and I find all these expected frequencies. And as a cross check, you can take total of this all the expected frequencies, and I have checked that this total is equal to this sample size 60. It must be equal to sample size if we have calculated expected frequencies correctly. So that is cross check for the calculation of expected frequency. Now I will check whether all the expected frequencies are at least 5 or greater than 5. Then here I find that in the last cell or last category, this expected frequency is less than 5. So I cannot apply chi-square test for goodness of fit test. So for that I have to combine these two categories. So if I combine these two categories, number of defects I will write as 2 or more. I will write categories in this way now, 0, 1 and 2 or more. So I will reduce one category here because this is less than 5, and I will take addition of these two expected frequencies. So that I have written in the next table. Similarly, I have to combine the last two categories in the given observed frequencies also. So I will combine here also. These 2 and 3 will be combined as 2 or more, and the corresponding frequency I will write as 13, addition of these two. So that I have written in the next table after that table. Okay, we were here, and now I combine these two last cells or last categories. So I have to take addition of these two also, and I have written here after combining. I have combined last observed frequencies also, which were 9 and 4. So their addition is written here, and this is addition of these two expected frequencies 7.974 and 2.424, and I have combined these two as 2 or more. So now we are going to use this table in the test statistic. Now the number of categories we will consider as first category, second category and third category, that is small k equal to 3. So remember, the number of categories in the formula of degrees of freedom are coming from the last table, in which we have taken care that all the expected frequencies have become greater than or equal to 5. Now in this table all the expected frequencies are bigger than 5. Therefore we are going to consider this expected and observed frequencies in the formula of test statistic. So the number of categories we will consider as small k equal to 3. Now the test statistic is sigma square of observed minus expected divided by expected. So we have to find out this quantity for each of these cells. So for first category I will take 32 minus 28.344 whole square divided by expected frequency, that is 28.344, that I have written here. This is for first category. Similarly for second category, this observed frequency is 15, expected frequency is 21.258 whole square divided by 21.258, and for the last cell 13 expected, this is observed, this is expected divided by expected. So the number of terms in the formula of test statistic must be equal to number of categories, which are 3 here. And I have calculated all these things using scientific calculator up to 4 decimal places, and I find that the value of test statistic is 2.9650. Now next step is to find out the critical value using chi-square table, and if in your question they have specified the table value, then you can directly use that table value. Now before that I have to decide the degrees of freedom. Suppose I am not given table value in the question, then to use the chi-square table I will require number of degrees of freedom. So that is equal to small k, that is number of categories, minus small p minus 1. What is small p? Small p is the number of parameters of the hypothesized probability distribution which are estimated from the sample data. The number of parameters which are estimated using the sample data is nothing but small p. Now in this problem we have estimated population parameter lambda of Poisson distribution using the sample mean. So the number of parameters which are estimated using sample data is small p equal to 1. We have estimated only one parameter of the Poisson distribution using sample data, therefore it is 1 here, and we have 3 categories. So we have 3 minus 1 minus 1, that is 3 minus 2, which is 1. So number of categories are, number of degrees of freedom are 1, and you can see they have written that value of chi-square distribution with alpha equal to 0.05 and 1 degree of freedom is 3.84, and we can check in the table also. Level of significance is 0.05. So we look here, and degrees of freedom are 1. So this is the row corresponding to 1 degrees of freedom, and if we go in this row up to this alpha, we have 3.841. that is correct value of chi-square distribution table. And if it is not given, we can use that chi-square distribution table as I explained. So the chi-square critical value is given, and it is 3.84, and we know that chi-square goodness of fit test is almost right-tailed. So I have sketched this shape of chi-square distribution just for understanding. This is chi-square critical value, and because alpha is 0.05, area to the right side of this point is 0.05, and this is the rejection region. And using table we have obtained that this point is 3.84. and what is the value of test statistic? It is 2.9650, or simply 2.96. So because this is 3.84, 2.96 somewhere here, and it is less than this value, therefore we are in non-rejection region, and therefore we fail to reject the null hypothesis. And what was the null hypothesis? Null hypothesis is that given population follows Poisson distribution. The population of the number of defects is Poisson. So we are not able to reject that statement that the number of defects in printed circuit boards follows a Poisson distribution. So in this way we can perform chi-square goodness of fit test. It is very easy, but you have to take care of certain things. First thing is you have to first decide the expected frequencies. For that you have to decide what is the probability mass function of hypothesized probability distribution. We will assume that our population follows particular probability distribution, so you must be familiar with the probability mass function of that probability distribution. Mainly we are going to consider binomial and Poisson probability distributions. After calculating probabilities for each category, we will multiply each of those probabilities by sample size, and we will obtain expected frequencies. Once we obtain expected frequencies, we will take care that expected frequency for each category is greater than or equal to 5. If it is less than 5 for some category, we will combine that category with the category which is in the neighborhood of that category, or we will combine with adjacent category, and we will take care that all the expected frequencies become greater than 5. And when we combine the adjacent categories, that will have to be combined for observed frequencies also. After that we will find out the value of test statistic using this formula. Now we will be having observed frequencies, expected frequencies, so we can easily calculate this sum. And once we calculate this value, we will find out the degrees of freedom using this formula k minus p minus 1, where k is the number of categories, small p is the number of parameters of the hypothesized distribution estimated by sample statistic. And here we have estimated mean of Poisson distribution using sample mean, therefore here small p was 1. And once we obtain number of degrees of freedom, and level of significance will be given. So using given level of significance and number of degrees of freedom, and using chi-square table, we find out chi-square critical value, and then we compare chi-square critical value and test statistic value. If test statistic value is greater than chi-square critical value, then we reject the null hypothesis. If test statistic value is smaller than this chi-square critical value, then we fail to reject the null hypothesis. So this is all about chi-square goodness of fit test. I hope I am able to explain this problem so that you can understand. If you have any questions, you can ask in the comment section. Thanks for watching.